All right, hello and welcome to the video for 3.6. So this is the last video in this section, and this is going to kind of be the culmination of everything we've talked about in the chapter. The whole chapter revolves around functions, and what we're going to do is look at some applications of functions, some situations where it would be advantageous for us to build an equation, which we're going to call a mathematical model. And we're going to use that model to predict values within that particular situation. All right, so let's start off and look at a first example here. So in this first example, it says we're going to be finding the distance from the origin to a point on a graph. Now in this particular case, the graph that we're looking at is y equals x squared minus 1. We can see that being graphed down here. Here's the parabola y equals x squared, shifted down 1 unit. And what we're going to do is we're going to kind of envision any point on this graph. So I could kind of slide this graph along slide this point along the graph of the parabola. And at each particular instant, like when the point is here, what's the distance to the origin? When the point is here, what's the distance to the origin? You can see that distance is going to change depending on where the point is. And what we want to do in this problem is we want to find that distance as a function of the x coordinate on the point. All right, so part A is asking us to do that. It says express the distance d from the point P on the parabola to the origin. We want to express that as a function of just the value x of this ordered pair on that graph, that point on the graph. All right, so the first thing we'll think about is like the distance formula, right? So let's think about, remember what the distance formula is. It's basically Pythagorean's theorem. But if we think of the distance formula in general, the distance between any 2 points is I'm going to subtract the x values and square them. And then I'm going to subtract the y values and square them. So in a very general fashion, the distance between x and 0 is going to be x minus 0 squared plus, and then y and the 0 would be y minus 0 squared. So our distance initially is the square root of x squared plus y squared. Now the problem with this formula is I have multiple variables in there. I have x squared and y squared, and I only want it to be a function of one variable. So in essence, what I'm going to do then is I'm going to replace the y with its expression. So I know that every point on this graph, the y value is the square of the x minus 1. So I'm going to replace the y with the square of the x minus 1. And then we've achieved, in essence, creating the distance function as one variable, a function of x. So if I, FOIL this out and do all that stuff, simplify this algebraically, this is what I end up with here. So here's the distance from the origin to any point on this particular parabola. All right, now one of the advantages to this is, suppose I want to find the distance where the point is x equals 0. So think about this for a second, right? If the point, I'm talking about the point x equals 0 on the graph, that's this point right here. So I'm finding this distance is what I'm finding. When x equals 1, I'm finding this distance here. When x equals root 2 over 2, right, I'm finding that distance. So x equals root 2 over 2. All right. So the advantage to this formula here is now I don't have to find the distance of every single point. I got a formula that's going to do that for me. All right, so now that we have the formula, this is going to be really easy to calculate. If I just plug 0 into this equation, I'm going to get 0 minus 0 plus 1. I get square root of 1, which is 1. I get that distance from here to here. That's pretty obvious that that's what that distance would be, right? I mean, this is a purely vertical distance. To go from a y of 0 to a y of negative 1, I have to move a unit of 1. So there's my distance 1. That was pretty obvious. I don't think I needed a formula for that, right? Excuse me. And then if I plug in x equals 1, I mean, it's kind of the same thing, right? To go from x equals 0 to x equals 1 on the graph, that's a horizontal distance of 1. Right? And I can see that if I plug 1 into here, I get 1 minus 1, which is 0, plus 1, which is the square root of 1, and that's 1. All right. Now, what if I choose some other distance, some other x value? So let's suppose I choose, x equals root 2 over 2. So now I'm just going to plug root 2 over 2 into this equation. I'm going to get root 2 over 2 to the fourth minus root 2 over 2 squared plus 1. That's going to give me square root of 3 over 2 as my distance. And of course, I could plug that in my calculator, get a decimal for that. Now, letter E says use a graphing utility, right? A graphing calculator. We could use Desmos, and let's find the value at which the point has a local minimum. So what is the minimum distance? So we're trying to find the minimum distance. Now, just visually speaking, I'm going to guess kind of like right here. Looks like this is about the minimum distance. So maybe like an x of about 0.5, 0.6. That might give us the minimum distance. But here's what we're going to do. We're going to plug this equation into the calculator, and we're going to find that minimum value. All right, so bringing up my calculator here, hitting the y equals button, I'm going to do the square root. So I'm going to do second square to call up the square root. Then I'm going to do x raised to the fourth. So I'm going to hit the caret key, x raised to the fourth power, and then I'm going to subtract x squared. So I get x, and I'll just use that shortcut, that square key, and I'm going to add 1. So if I hit graph here, here's what that graph looks like, right? And not a really good view, right? Let me zoom in. Let me do a zoom decimal. Zoom decimal is kind of a nice window to choose. Zoom decimal. I get a little better of a graph. I can see here's a local minimum. Right? Here's a local minimum as well. All right, so that kind of makes sense, right? I mean, if this is a minimum distance, this will be a minimum distance as well. So if x equals like 0.6 gives me a minimum distance, negative 0.6 will as well. All right. So I know I have some symmetry to here's my distance equation, right? So I'm going to zoom in. I'm going to find the maximum. We talked about how to do that in a prior video. I'm not going to take the time to do that in this video. But if I were to use the min feature, I were to find the minimum, here's that point. So it looks like about 0.71 is the x coordinate. So about right here at 0.71, if I come down to the graph, that's going to be a minimum distance. And then obviously negative 0.71 would give me the same, right? But what they asked me for in this particular problem was only give the positive x value. So x equals 0.71 would give me the minimum distance. And then remember, for this equation, these are the distances. Right? I graphed my distance function, right? This is the function I plugged in. So my minimum distance would be about 0.87 units of distance, whatever my unit is here, inches, meters, miles. They didn't really tell me, right? Right, and I just wanted to jump back to this example real quick because I think, what I have seen with students, what the hardest part of this section is the first part, building the function, building that equation, right? So this question asked me to express the distance as a function of x, right? So when we had to go through the process of building that equation, right, that's really the hard part of these problems. So you want to be really patient with yourself. You want to give yourself the time that you'll need to work through building that equation. That's a struggle, and that really takes some practice. So let's work on that together in this video here. So let's take a look at a second example. So in this example, it says that a rectangle has one corner on the graph of the parabola 25 minus x squared, and another at the origin, a third on the positive y-axis, so here's a point on the positive y-axis, and then a fourth on the positive x-axis. Well, the first thing it says, letter A, express the area A of the rectangle as a function of x. All right, now again, I think this is probably the hardest part of these problems. How do I do that? Right? Now, first of all, before we jump into that for this problem, I just want you to kind of see if you can visualize what's going to happen here. All right, let me see if I can bring up my little drawing cursor again. I'm sliding this point along the parabola. So if I stop the point, let's say right here, there's going to be a horizontal and vertical line that creates the rectangle. I'm finding the area of that rectangle. If I slide the point up here, there is a horizontal and vertical line that creates the rectangle, and I'm finding the area of that rectangle. So what we're wanting to do, based on the x value that we stop to find that point, based on this x value that we stopped at to find that point, based on this x value that we stop at to find that point, we want to create the area as a function of just that x value, right? Now, if you think in general, right, the area of any rectangle is, length times width, right? But in this particular case, like if we look at this square right here, let's say the one dimension is that x value. So let's call that, let's maybe call that the length. There's one of my dimensions. And then the width is, let's call that the height of the rectangle, right? Now, obviously, I can use the letter y, but I'm wanting to get this all solely as one variable. So x times y is my area, but my y value is 25 minus x squared. Right? So that's what I'm going to plug in as my y value. And there's my area formula. Right? So if I distribute x times x squared is negative x cubed, and then x times 25 is plus 25x, right? So there is the area function, right, if you will, for the area of this rectangle on this particular graph in this particular scenario. And again, I think this is probably the hardest part of this problem, and I think my tips for you would be the following. If they're asking you to find like area of a circle or area of a rectangle or area of a triangle, start off with the general knowledge. What is the area of a rectangle? Oh, it's length times width. And then based on your scenario, try to figure out what length and width are in terms of that one variable. Area of a triangle is 1/2 base times height. All right, so draw the picture, visualize the problem, and try to determine what the base and the height are in that case. Right? And again, this is going to take practice. Right? Be patient with yourself. All right, now so part B says, what's the domain of this function? And a couple different ways that we could approach this, but I think the easiest way is to just think geometrically. Right? We have written the area as a function of x. Right? X is this distance here. So we're never going to let x go in this direction. We're not going to let x be negative, right? Where they told us this had to be in, the first quadrant, right? So x is going to be greater than 0, and then x can't be any bigger than 5, right? So just geometrically speaking, right, part B here, the domain right here, right? The domain is going to be from 0 to 5. So I could write that as an inequality, right? Or I could write that in interval notation. But that's going to be, oops, let me use a bracket because I'm including the endpoints here, right? Now, those endpoints aren't very interesting rectangles, right? I mean, if I slide this point down here all the way to x equals 5, there really is no rectangle, right? It's just kind of a flat rectangle with no area. But, technically, I could let it equal 5. It's just not very interesting. Okay, so then letter C says graph the equation. So let's graph this area equation. So like y equals negative x cubed plus 25x. So if I take out my graphing calculator and I graph y equals negative x cubed plus 25x, right, I'm going to see this basic graph. Now if I graph on this particular domain, right, that's what I'm going to see there. So what I did in my graphing calculator, let me bring that up real quick. What I did in my graphing calculator was I plugged in the equation, let me use the negatives key down here, negative of x raised to the third plus 25x, and then I went to my window, I did an x min of 0 and an x max of 5. I only wanted to graph over the domain that we have for this function. So when I graphed, I don't see the y value really well. So at that point, here's a cool little trick. Once you set the domain in your window, once you set your x min and x max, you can go to the zoom and you can do the zoom fit feature, and it'll fit the y values to your specified x min and x max. And so there's the picture that we got there, right? Now, obviously, if you're using Desmos, it's a little bit easier to adjust the graph window. The calculator is a little bit more of a pain to adjust the window. And then the last question is, what's the largest value? So again, I'm not going to take the time to do this in this video, but I could use the maximum feature to find the maximum of that graph. And if I were to do that, this is the point that I would locate. Now again, I want to remind you here that the x value and the y value have particular interpretations. So remember, the x value is this x value on the graph, right? Where should I place the x value to choose the point so that I get the maximum area, right? The largest area. And then this graph that we created was the area equation. We graphed the area equation. So this y value is the largest area, right? So again, this is saying if I choose x to be like 2.89, if I round, if I choose x to be like 2.89, then the largest possible area I'm going to get out of this scenario is 48.11 square units. I remember area as square units, right? So square feet, square inches, square meters. I'm not sure what the unit is in this case. All right. So another reason why in 3.3, when we talked about max and min values, we were really careful to, kind of differentiate between the x value of the max and the y value of the point. So the x value has a particular interpretation. The y value has a particular interpretation, especially when we get to these word problems, right? So this y value, this was the area function, so that's the maximum area. And then the x value were these, these distances here, right? The x on my graph. All right, so look, in this next example, I just wanted to take a little bit of time to just kind of practice. Again, what I said was the hard part of these problems. So here's another example where we're going to just build the equation. We're not going to find a maximum or minimum here. We're just going to build the equation. So this problem is that a semicircle of radius r equals 7x is inscribed in a rectangle. So the diameter of the semicircle is the length of the rectangle. So again, keep that in mind. The diameter of the semicircle is the length of the rectangle. And you can see, hopefully, in a visual sense, this radius that we have here, right, this radius is half of the length of the rectangle. So if I double that radius, right, I got 7x and 7x here. I got 14 x's that make up the length of the rectangle. And then again, this radius is going to extend here as well, right? There's my radius of 7x, and that's going to be, let's say, the height of the rectangle. So I've got a length and a width, or length and height, however you want to call that, right? So one dimension of the rectangle is 14 x's. The other dimension of the rectangle is 7 x's. So when we're being asked to express the area of the rectangle, we're going to multiply length times width, and that's going to give us the area of the rectangle. So if we do the area of the rectangle, length times width, we got the 14x times the 7x. 14 times 7 is 98, and x times x is x squared. And so there's our area function. Now, when we're asked to do the perimeter, keep in mind what perimeter is, right? Perimeter is the distance around the figure. The distance around the figure. So I'm finding the perimeter of the rectangle. I'm going to have, the length twice. I got two lengths, and then I got the width twice. I got two widths, right? So my perimeter is 2 lengths plus 2 widths. And then for this particular scenario, that's 2 times 14x plus 2 times 7x, which is going to give me 42x. All right, so I think I got one more example I want to do here, but I just want to point out to you in all of these examples, right, when I'm calculating a quote-unquote function of one variable, the key is to start with the general piece of knowledge. Start with the knowledge that the area is length times width. And then for that scenario, figure out what length and width are in terms of that one variable. That's the hard part. In this case, we're asking for perimeter. What's the perimeter of a rectangle? 2L plus 2W. And then make the leap to one variable. Again, it takes a lot of practice. Be patient with yourself here. All right, so let's take a look at this one last example. And this one's a little bit more challenging, so I wanted to take the time to work through something like this for you. You're going to see something really similar to all of these problems in the homework. So just wanted to do this one. This is probably one of the more challenging ones out of these group in this section. So this problem says that 2 cars are approaching an intersection. One is 4 miles south of the intersection and is moving at a constant speed of 20 miles per hour. The other is 1 mile east of the intersection and moving at a constant speed of 30 miles per hour. So it says express the distance between the cars as a function of time. All right, so I'm going to visualize this as like in an XY plane. Okay, so the first car is 4 miles south of the intersection. So if this is the intersection of the two roads, I'm 4 miles south down here. So let's say I'm at 4 miles. Now technically this would be -4, right? -1, -2, -3, -4. But I'm 4 miles south here. Okay, excuse me. Now I'm moving at a constant speed of 20 miles per hour. So this point is moving in this direction, and it's moving at 20 miles per hour. Okay, so that's the information I have here. That's sloppy. That should say mph. 20 mph is how that's moving. Now at the same time, the other car is 1 mile east. So let's say this is east and we're 1 mile east. So here's where that car is, and it's moving towards the intersection at a speed of 30 miles per hour. All right, so there's kind of the information given to me here. And what they're wanting is the distance between the cars. So let me change color here, and let's change to like yellow. So what I'm finding, I probably won't do a very good job here. What I'm finding is this distance here, right? I'm finding that distance between those 2 points. Now obviously as this car moves, and as this car moves, that distance is changing, right? So what we're wanting to do is find that distance, excuse me, find that distance of that hypotenuse, if you will, as those cars move towards the intersection. All right, now let's think about this for a second in terms of just each car. Excuse me. So we know that this car is located 4 miles south, right? Goodness gracious, excuse me. And it's moving 20 miles per hour. So let's say after 1 hour, where is the car? Well, after 1 hour, it has moved 20 miles per that 1 hour, right? So I would literally take the 20, multiply by the 1 hour of travel, and then I'm going to add that to here, right? So this point is going to be -4 plus 20. He's going to have moved up 20 units in this direction, okay? Excuse me. After 2 hours of travel, he's gone 20 miles per each hour. So 20 times 2 is 40. He's gone 40 miles in those 2 hours. So I've started at this point. I'm going to add 40, and I'm going to move up to here somewhere, right? It would be, what, 36, right? After 3 hours, same thing. After 3 hours, I've gone 60 miles. So I'm going to take -4 plus 60, and that's going to take me way up on the y-axis, right? At what would that be? At 56 is where I'd be on the y-axis. So I think in terms of an ordered pair, over time, the x-coordinate is always 0, but the y-coordinate is growing. So over time, this point is at an x-coordinate of 0, and it's at a y-coordinate of -4 plus 20 times the time t. Right? So that would be like the y-coordinate of that point. Okay. Now, think of this point. Where is it? All right. So the y value is always 0 on this line. So the y value of this point is always 0. That's not changing, but the x value is changing over time. And again, same kind of thing, right? We're starting at 1 mile. After 1 hour, I've traveled 30 miles. So I'm 30 in this direction, which would be 1 minus 30, and would put me out here at -29. Right? After 2 hours, I've traveled 30 times 2, which is 60 units in this direction. So I'm at 60, excuse me, I'm at 1 minus 60, right? I'm at 1 minus 60, okay? That would give me the -59 that I would be at. So in general, after t hours, I've traveled 30 times t, and I'm going to have 1 minus the 30 times the t. That's going to be the x-coordinate there. Now, the reason that I made these ordered pair connections is because now I can use the distance formula. Right? Remember, I'm trying to find the distance between these 2 points over time. Right? So remember, in general, the distance formula is, the change of the x's, and I'm going to square that result. This is coming out sloppy, I apologize. And then the change of the y's, y2 minus y1 squared. And then I'm going to square root that whole number. Okay? So when I look at these two ordered pairs, the change in the x's, I'm going to have 1 minus 30t minus 0. And that's going to get squared. So I got 1 minus 30t, and then, subtract 0. And that gets squared. Right? And then the change in the y's. So I'm going to have 0 minus this number. Now remember, if I do x minus this number, I have to do 0 minus this number. Right? So if I do 0 minus this, that's going to become 0 minus negative 4 plus 20t. And I'm going to distribute the negative. So I'm going to have 4 minus 20t that is going to get squared. Okay? So that's a 4. Right? This is my distance as an expression of time. All right, now I could FOIL all of this stuff out. I could FOIL all of this stuff out and get a result. So let me do that. Let me pause the video and do that for you. All right, so I just want to remind you of a little shortcut, right? When you're FOILing, right, when you're squaring two terms, a binomial, I square the first, so 1 squared is 1. I square the last, so 30 squared is 900. T squared is t squared. And then I multiply these two and double. So 30 times 1 is negative 30. And then I double that, negative 60t. Right? And then I square the 4, get 16. Square the 20, get 400t squared. And then 20 times 4 is 80. And I double that, negative 160t. And there's all of those terms. And then I'll combine the like terms here. All right, so 900t squared plus 400t squared is going to be 1300t squareds. And then I got the negative 160 plus negative 60 is negative 220t. And then I got the 16 plus 1, which that's wrong. That should be 17. All right, so there's my distance right here as a function of time. All right, now remember, as you work on these, if you got questions, post on the discussion board and we can help each other out.